Last section to cover.
Yay.
So that's kind of good. Tomorrow review and test the next day. This section is in 6.1. It's on the area between curves, which sounds kind of cool. And if you look at the notes, there are some pretty cool problems that we'll do. Like I mentioned a minute ago, the cool part about this is very immediately applicable in your 1220 class, because they pick up this class right where we leave off in chapter 6 and start talking about how to find more difficult areas and even volumes. And I think if you think about the problems this way, the way I teach you to think about them, I think you're going to be much better off in the long run. And I think it's easier to understand some of those complicated problems that they'll do in 1220. So this is going to seem like I'm kind of belaboring the point and making things more complicated than they need to be. But I think, again, if you think about this way in the long run, you're much better off. So the starter question there says, what is the differential expression for the width of that rectangle? So I've got this area represented, which is actually just a copy of some of the problems that we've done before. So I've got this area represented right here from A to B underneath that curve, between that curve and the horizontal axis. And then I've got this little thing, I'll call it a representative slice of area, a little rectangular slice of area, which we're going to use to kind of figure out, well, how would I find out all of this area? Well, this width right here is a difference in x's, so we're going to call that dx. So that's going to be the width of that little rectangle. And then how tall is the rectangle? How far is it from here to here? F of x. Okay, so we're going to use f of x. We're going to use the function to represent the height. Okay, and then I've got this question that says, how do you know how tall it is? Well, we never concerned ourselves with this before, thinking about, well, how tall is it? We just said it was always the function height. Okay, but why is it f of x tall? Why can you say the function, or the height of that rectangle is the function value at that point? Why is it something else? Why isn't it taller than that? Why isn't it shorter than that? Yeah.
Is it just because we always have it like function with the origin, so it's like always on the x-axis? That's always the bottom.
Okay, key right there is the x-axis. The bottom is always the x-axis. So how do you know how tall it is? We're going to say this, because we know the bottom is the x-axis. We know where the bottom is. Okay, we know the bottom is y equals 0. So if we've got this function height up here, if we've got this point right here that's f of x above the x-axis is 0, we're going to be precisely f of x units above the x-axis. So the short of this is, we know where the bottom is. The bottom's at 0. Okay, and we're going to change that just a little bit in a second. So we're going to take a look at this next part. So we'll see if we can fill this in. It says, remember, the definite integral is asking for the signed area between the curve and the x-axis, or between the curve and the horizontal axis. It says, recall that there is a difference between the area and signed area. Okay, area is always positive. So if we're finding area, if it says area, we're finding a positive value. If it says signed area, or what was the other way? Net area. Okay, then it can be positive or negative depending on a couple of things. It depends on what the function values are. It depends on the interval, and it depends on the direction of integration. Okay? So we're going to look at this a little bit more closely. So we're going to just set up, we're not actually going to evaluate this, but we're just going to set up an integral to find the total area between this function right here and the x-axis from x equals 0 to x equals 2. So because this function is always positive, and I've got a picture of what this looks like right here, so we don't have to pull out our graphing calculators or anything, okay? The easiest way to do this would just say, well, I'm going to have the definite integral. I'm going to add up this area right here by using a definite integral from 0 to 2. Start slicing this up at 0 and stop slicing at 2 for that function right here. Here's the height and there's the width. Okay? So we know how area functions work. We know a definite integral will accumulate that area. But here's what we want to do. Okay? We're going to actually draw a representative slice of area. And we're going to remind ourselves of why it looks like this. Okay? This is dx units wide. It's f of x units tall. And the reason we know that it's that tall is because the bottom of this is at y equals 0, or at f of x equals 0, if you wanted to think of it that way. So that little representative slice looks like this. I'm going to take that top function, x to the fourth minus 4x squared plus 5, and I'm going to subtract where the bottom is. The bottom was 0. Now that looks like a really silly thing to do. This is the top of the rectangle, and then if I subtract where the bottom is, that should tell me how far it is from this top point down to this bottom point. Right. Silly thing to do on this problem, but that will tell me how tall it is. These two things together will give me the height of the rectangle, and then the width is what we normally have, just dx. And where do I start adding up these rectangular slices? I start adding up those rectangular slices starting at 0, and I stop when I get over to this point right here. I stop when I get to 2. Now, is this that I've got right here, this ugly mess that I made much more complicated than it needs to be on this problem, does that equal this thing over here? It does. Okay, it's the idea that's important there. The fact that we can figure out how tall this rectangle is by figuring out where is the top of the rectangle. It's up here at f of x on the curve, and the bottom of the rectangle is on the x-axis. It's at 0. So if I want to know the distance from the top to the bottom, I take the top and I subtract the bottom. Does that make sense? Okay. So we can apply that idea to any set of functions. So this little theorem says if f of x and g of x are continuous on this closed interval from a to b, and it says f of x is greater than g of x. So that's on the top, and that's on the bottom. Then the area, and notice it says area, it doesn't say net area, it says area. Okay? The positive area between the curves is the definite integral from a to b, f of x minus g of x dx. And if you want to put brackets around that or parentheses or something like that, that would be fine. Again, these two things here where we've got the top minus the bottom, that would represent the height of the rectangular slice. And this dx, again, would be the differential. That would represent the width of that little rectangular slice. Does that make sense? So let's go ahead and find the area between that same curve I showed you just a second ago and y equals -1 on the interval from 0 to 2. So again, we're going to start by drawing a little rectangular slice. So here is that slice of area. It could be drawn right next to this one. It could be drawn in the middle. It could be drawn on the end, because that just represents all of the little slices that we're going to take in order to accumulate this area. Okay? So we're going to do this. We're going to integrate. We're going to slice from 0 to 2. And I'm going to take the top function. The top function is x to the fourth minus 4x squared plus 5. And then I'm going to subtract the bottom function. Now, what is the bottom function?
-1.
-1. So this right here is the height, and this right here is the width, or dx. Now, the answer to this has got to be more than the answer to this one up above, right?
Right.
Because I've added this little slice of area down on the bottom, this little rectangular region right there. Okay? So, because it was below the x-axis and I did top minus bottom, what happens when I simplify this? Yep, it's going to turn into a +1.
Wouldn't it literally be just 2 units bigger?
It would be, okay? Yep. But since we don't know the answer to this one, we can't just add 2. Okay?
Oh yeah, what is
Okay. So Juan just pointed out, wouldn't the answer to this one just be 2 units bigger than the answer to this one? And the answer
Yeah.
to that is yes. But because we didn't compute this one, we can't just add those 2 units. Because this is 1 unit tall and 2 units wide. This isn't to scale. I adjusted the scale so we can see.
Area of top plus 2.
We could. All right. So no more shortcuts.
Oh.
0 to 2, x to the 4th plus 4, whoops, minus 4x squared. And then I'd write, this is going to be 5 plus 1, so I'm just going to write plus 6 dx. And then I can go through and I can actually run through and do the computations. So we're going to integrate this, so we'll find an antiderivative. So that's going to be x to the 5th over 5 minus 4x to the 3rd over 3 plus 6x, and we'll evaluate from 0 to 2. Good there? The nice thing is we've got an x in each one of these, and we're plugging in a 0 for the lower limits. So this is going to be 2 to the 5th over 5 minus 4 times 2 to the 3rd over 3 plus 6 times 2, and then minus, what do I get when I plug in a 0? I get a 0. So I'm going to have 32 fifths plus, let's see, this is going to be, that's going to be a minus 32 thirds, and then plus 12. So I'll get a common denominator of 15. So that's going to be 96 over 15. 160 over 15. And let's see, 12 times 15.
15.
12 times 15, so 180, right? Correct?
That would be plus 180.
Oh, yeah, plus 180, thanks. Just looking at that thinking that better turn out to be positive because we're finding an area. Let's see, so if I subtract here, so that's going to give me positive 20 fifteenths. So I get 116 fifteenths. Okay. Any questions? Top minus bottom guarantees us that we're going to have a positive height. Okay, and again, we're integrating in a positive direction, so we're going to have a positive width. Okay. What if?
Y was some function.
What if I had something like this? What if I had a function that was down below here and another one here? So here's my g and here's my f.
Oh, no.
If I do top minus bottom, do I still get a positive answer? Yeah, let's pick a number. Let's say this is -3. Let's say the function value right here is -3. And let's say the function value here is -10. Top minus the bottom, I end up with +7. It will always, if you do the top minus the bottom, it will always produce a positive quantity for the height. Okay? Any questions? Okay, go ahead and flip the page over then. Okay, on this next one, we're going to use the same couple of functions, but we're going to look at this in several different ways. So this is just kind of a classic problem. I would definitely know how to do something like this. It says, find the area bound by cosine of x, sine of x, and the y-axis in the first quadrant. So let's think about what that would look like. I'm going to do cosine, and then I'm going to do sine in, oops, change colors here. I'll do the sine in blue. Okay, and we'll do the y-axis in green. So here's what the cosine looks like. Remember, the cosine starts at 1 and then hits 0 and then hits -1 by the time you get to pi. So it looks something like this. The sine starts at 0 and goes up to 1 and then back down to 0. So the sine looks something like this. And then the y-axis, of course, is right here. So this little region right here is what I'm after. I want to find the area of that region.
What area?
This area right here. So let me shade it in. That area right there.
But the first quadrant.
Over here?
No, never mind.
Over here?
Just keep
Okay. So it's got to be bounded by the y-axis, so it's got to start right here, okay? The cosine and the sine, okay? This stuff over here wouldn't be part of the shaded region that we're finding because that's not bound by the y-axis. Yeah.
Okay, now, so the first quadrant is from 0 to pi half, so wouldn't we have that second part shaded in?
Where?
Where
He
the,
just answered right.
Yeah,
It has to be on the y-axis.
Yeah. It has to be bound by cosine, sine, and
okay.
y.
All three of them. That's the only part on this graph.
Okay.
Even if I did this stuff over here,
Uh-huh.
through the rest of this, oops,
No, I'm
change
talking
colors.
like from 0 to pi halves, all that area.
This
Yeah.
stuff underneath here,
But that, yeah.
no,
that-
because then that would be
Okay.
bound by the x-axis.
Okay.
Okay? So is everybody clear on this? Why that's the area?
Yeah.
Okay. So again, I would stick with this idea now, and I would stick with this idea when you get into 1220. Draw a representative slice of whatever you're trying to find. We're trying to find this area right here, so I'm going to draw a little rectangle there. The width of that rectangle is very easy to find. It's just the differential dx, because remember, we're going to take thinner and thinner slices, like we did at the beginning of chapter 5. Okay? And now I want to figure out how tall this is, because I'm literally finding an area of a rectangle, so I need to know how tall it is. Well, the top function is the cosine. That tells me where the top of the rectangle is. What tells me where the bottom of the rectangle is? The sine. So this is going to be, again, I need a height, so this is going to be the top, which is cosine x, minus the bottom, which is sine x. There's the height. There's the width. Where do I start slicing these little rectangular slices?
0.
At 0, and where do I stop?
Pi 5.
Okay, very good. It's pi fourths. When does the sine of x equal the cosine of x in quadrant 1? Okay, pi fourths. So this would be pi fourths. So let's go ahead and figure this out. We better get a positive answer to this. And let's see, let's maybe make a rough estimate. This is 1 unit tall, and this is pi fourths. Pi fourths is about 0.7. So this rectangle that definitely encloses my region would be about 0.7 times 1. So approximately 0.7. And we don't even come close to using that whole thing, do we? So we're expecting something somewhere in the neighborhood of maybe 0.35-ish, somewhere around there. Okay? So let's go through and do the calculations and see what we end up with. Antiderivative of cosine is? Sine, very good. Antiderivative of negative sine? Cosine. Now, don't get too carried away. Double check and make sure you have the right antiderivative. By now, we're pretty good at evaluating definite integrals. If I differentiate sine, do I get cosine? If I differentiate cosine, do I get negative sine? Okay, is that the right answer? Yes, it is. Okay, we're going to evaluate this from 0 to pi fourths. Now, sometimes we'll get in the habit of, well, the lower limit's 0, so I don't even have to evaluate that. Is that the case with the trig function? No, we better be careful. Let's evaluate the whole thing. So this is going to be the sine of pi fourths plus the cosine of pi fourths minus what I get when I evaluate it at the lower limit. So that's going to be the sine of 0, sine of 0 plus cosine of 0. I have a hard time writing a 0 without trying to make it a theta when I'm dealing with trig functions. Okay? Sine of pi fourths? Radical 2 over 2. Same for cosine. Minus 0. Yeah. Okay. So if I were to distribute through, I'd get minus 1, right? So these two together make a radical 2. Minus a 1. So there's the exact answer. Let's throw that in the calculator and get a decimal approximation and see how close we were. We were guessing somewhere around 0.35. This is about 1.414 minus 1, so this should be 0.414. Right? Not bad. Good ballpark estimate. Good clue that we're headed in the right direction. Okay, any questions there? Okay, let's take a look at the next one. Notice that the functions are the same. but the interval is different. So the area bounded by the cosine of x, the sine of x, on this interval. So again, I'm going to do the cosine in red and the sine in blue. So the cosine starts up here, down here, and like this. So we've got something like this. And then the sine starts here, up to here, and then down to there. So here's what the sine looks like. We want the area bound between the two of these, between 0 and pi. Now, we've got to be a little bit careful because notice that a rectangular slice right here has a top that's cosine of x and a bottom that's sine of x. Can I slide that same rectangular slice through the whole thing, and does it represent the entire interval? It doesn't, because on the top here, or on this part of it, the top is sine and the bottom is cosine. Okay? Split this up into two integrals. Okay? So the first one is going to be the integral from 0 to pi fourths, top minus bottom, whoops, cosine x minus sine x dx. Then we're going to add what we get when we find this area, because remember, the way we're structuring this, we're guaranteeing that this is going to be a positive quantity. So let's think about what that slice looks like. The top is sine, minus the bottom, which is cosine. There's our height of that slice. There's the width. Where do I start slicing for this representative slice, and where do I stop? Start at pi fourths, start right here, take over at that intersection point, and I stop at pi. Okay, we already know this answer here, right? We already know that that's radical 2 minus 1. So we're going to kind of put that in our back pocket, and let's evaluate this one. I need an antiderivative here. Is that right? Differentiate negative cosine, you get positive sine. Differentiate negative sine, you get negative cosine. So is this the right antiderivative? Yep. So then I need to evaluate from pi fourths to pi. So let's see what we get. I get minus this, whoops, cosine of pi minus the sine of pi. Okay, and I do like, when it gets, I mean, when there are these many negatives floating around and I've got to evaluate trig functions and stuff like that, I do like to put the second one in parentheses. So this is going to be negative cosine of pi fourths minus sine of pi fourths. Let's see, cosine of pi, negative 1, so this is going to be a 1, right? Minus minus 1. Sine of pi is 0. This is going to be, I'll do a little bit of work here. Make that a little bit easier. So I get a 1, and then I get plus radical 2 over 2, radical 2 over 2. So I'll bring down that original answer right here. So I had radical 2 minus 1 and then plus the 1. So these guys will go away. Okay, this is from that original integral right here, right? Is that okay? So I get radical 2 from this one, and I get radical 2 from this one. So I get 2 radical 2 as an exact answer, and roughly 2.8-ish for that one. Okay, any questions? Top minus bottom guarantees that the height of our rectangle is positive, and we usually integrate in a positive direction, so that'll guarantee that our width is positive. So we're guaranteeing that positive area that we talked about. Okay, go ahead and flip the page over. Let's take a look at example 5. We're going to do this same integral several different ways. So this says, find the area in the first quadrant again, bound by y equals the square root of x and y equals x minus 2. So I'm going to do this one in red, and I'll do that one in blue. So let's think about what this looks like. Square root function, top half of a sideways parabola. I'll just draw some convenient points right here. Looks like that. Just a line crosses at -2 on the y-axis and then has a slope of 1. So it's going to go like this. And then the region we're interested in is what's bound by those two curves in the first quadrant. It's this area right here. Why isn't it this chunk right here?
The height's determined by.
Yep. Okay. There's nothing below this. Okay. If I'm going to shade this in, I might as well shade all that in. Okay. Now I just realized I should probably be a little bit more specific. I should say between the two curves and the x-axis, because I guess technically this stuff up here would be between the two curves and they would still be in the first quadrant. Okay. Just realize that. Okay. So let's stick with this right here. Stuff bound by those two curves in the first quadrant and got to be bound by the x-axis as well.
Stuff underneath the x-axis?
Would we count this? Not in the first quadrant. Okay? So really think about it as you're drawing that region and identifying what we're going to do here. Question? Okay. Okay. So if I'm going to do this problem and I'm going to draw a rectangular slice, I can draw this slice right here. Top minus bottom, pretty easy to figure out. Is that representative throughout the entire interval where I need to accumulate this area? It's not, is it? Okay, so I need to do the same thing I did before. I'm going to take this and I'm going to break it up. So I'm going to use the square root of x. That will give me the area if I start at 0, and where would I stop right here? Stop at 2. It intersects the x-axis starting right here at 2. And then I would add, I need to have another slice over here. So this little rectangular slice represents all the slices from 0 to 2. This one is going to represent from 2 all the way to where they intersect over here at 4. So we're going to go from 2 to 4. Top, square root of x, minus the bottom. What's the bottom? And I would put that in parentheses because that's got more than one piece. There's the height of our rectangle. There's top minus bottom, and then dx. So what we're after is the integral from 0 to 2 square root x dx plus the integral from 2 to 4 square root x minus x plus 2 dx. With me? Any questions? Okay, let's go through and do the calculations. Remember, this is going to be thought of as x to the 1/2. So I'm going to increase the exponent by 1, divide by the new exponent. So that's going to be 2/3 x to the 3/2. Which, if I were going to evaluate, I probably wouldn't write it that way. So let me write this up above here. I'm going to write that this is 2/3 x to the 3/2. So I'm going to write 2/3 square root of x cubed evaluated from 0 to 2. Okay, then we'll do this one. This is going to be the same antiderivative, so this is going to be 2/3 square root of x cubed minus x squared over 2 plus 2x, and I'm going to evaluate that one from 2 to 4. Any questions there? So if I plug in a 2, this is going to give me, let's see, yeah, cube at first, we'd have square root of 8, pull a 2 out. So this is going to be 4 radical 2 over 3. Let's see, if I plug in a 4, that's kind of nice as far as the square roots go. So this is going to be what I get when I evaluate this guy. Well, let's see, I don't need to set a parentheses. Yep, so that's going to be square root of 4, 2, cubed, that's 8, times 2, so that's going to be 16 thirds. 16 over 2, so that'll be minus 8. Plus 8. Minus, and I'm definitely going to use a set of parentheses here. I'm going to plug in a 2 into this one. I'm going to get the same answer I had right here. So that's going to be 4 radical 2 over 3. Plug in a 2 here. That's going to be 4 over 2. So that's going to be minus 2. And that's going to be plus a 4. How are we doing so far? Okay, we get a couple nice things that happen. We'll take care of these right now. Let me go ahead and distribute through. So this is going to be a negative here. That's going to be a positive, and that's going to be a negative, right? Those go away. Those go away. And let's see, I get 16 thirds. 16 thirds minus 2. So that's going to be 16 thirds minus 6 thirds. So that's going to be 10 thirds is our answer on that one. So after that big mess, we end up with a relatively nice answer of 16 thirds. Any questions? That's a pain.
That is.
Huge pain.
Is there going to be an easier way?
Yep.
Oh,
I'm going to show you 2 easier ways right now.
No way.
Okay? So some of you noticed on the back page there's some pretty funky looking graphs, and we're going to find some shaded areas. We're going to kind of introduce that idea right here by thinking about this. Could I find this area? So let me draw these curves again. Could I find this area using one single integral? So this is the area that I'm after right here. Could I do it using one single integral? Well, we use integrals to add up these rectangular slices. And the problem that we had up above was, if I draw a rectangular slice like this, I've got a different top and bottom for each of these little intervals right here. From 0 to 2, it's one top and bottom, and from 2 to 4, it's another top and bottom. Why am I stuck drawing my slices like that, though? Couldn't I draw a slice like this? Is that possible? Could I mean, if I draw that little rectangular slice, could I figure out a height and a width? And if I slide this slice down here and up here, don't I have the same kind of representative as far as height and width? I do. But now I've got to be clever about this, because think about the beginning of chapter 5. When we drew slices, we sliced it up and we added them up and we said that was an approximation for the area. The idea of finding the actual answer, we needed to make our slices thinner and thinner and thinner. So if I make these slices thinner and thinner and thinner, okay, normally we represent that thin thing with a differential, usually a differential of x. But we're not slicing this in the x direction anymore. What direction are we slicing it in? The y direction. So we're going to use dy for a width. And then in order to figure out this positive width, height, hopefully I said height, dy is going to be the height. The width of this rectangle is going to be the right minus the left. If I take a right function and subtract a left function, that's always going to give me a positive. Okay? Now, here's the issue that we run into here. This function is y equals the square root of x. And this function right here is y equals x minus 2. If I'm going to use a differential of y, I need to write this as x is a function of y and x is a function of y. So here's how we're going to think of this. I'm going to write this as y squared equals x. or even better, x equals y squared. And I'm going to think of this other function right here as x equals y plus 2. So now I need a width and I need a height. How wide is it? Right minus the left. So this is going to be y plus 2 minus the left, which is y squared. And how tall is it? dy. Okay, I've got everything in here, the integrand and the differential, all written in terms of y. I'm going to slice from here up to here. So if these are functions and differentials of y, I need limits in terms of y. I'm slicing in the y direction. Where do I start slicing? 0, and where do I stop? Stop at 2. So take a good look at this. I'm going to clean this up just a little bit. Y plus 2 minus y squared dy, integral from 0 to 2. Take a look at that and the mess we had before, and think about the integration here. Y squared over 2 plus 2y minus y cubed over 3. And look at this. Power functions evaluated from 0, that's nice for a lower limit, up to 2. So this is going to be 2 plus 4 minus 8/3 minus, what do I get when I plug these in? 0. So this is 6 minus 8/3. In thirds, that's going to be 18/3 minus 8/3, which is, lo and behold, 10/3. Which was the easier setup and integration? Once you got used to the idea that we can write everything as a function of y and then do right minus left to make sure we have positive answers. And notice we're integrating in the positive y direction. We're integrating up in the positive y. Okay? You want one more? This is the coolest and this is the cleverest. Okay? What if we use geometry in a single integral? So take a good look at what's going on here. I've got this shape and I've got this shape. What if I did this? What if I said, you know what? It's pretty easy to go from 0 to 4 square root x dx. That's the whole thing. But I don't want this guy right here. What shape is this? A little triangle. I want to take off that triangle. That triangle is 2 units wide and 2 units tall, right? So it would be half of 4, so it would be 2. Okay? There's an integral minus a triangle. And this was pretty easy to integrate. If I integrate that, again, that's x to the 1/2, so that's going to be x to the 3/2, 2/3, evaluated from 0 to 4, minus 2. Or that's going to be 2/3. This is the square root of x cubed, evaluated from 0 to 4, minus 2. Plug a 4 in. Square root of 4, 2, cubed, 8, times 2, 16 thirds. Plug in a 0, 0 minus 2, and look at that, 16/3 minus 2 again, so that's going to be 16/3 minus 6/3. 10/3 will be our answer again. Okay? Any questions? Okay. Is this the last page? It is. Good. We got time. Okay. So problem number 31, I think, is on your assignment, or it's very much like one on your assignment. And I haven't seen this in too many textbooks. I mean, absolute value is a pain in the butt. Okay. The idea that they're getting at here is they want to guarantee that this quantity is always positive. So what they're really doing is they're making sure that we find the area between these two curves on this interval. We're integrating in a positive direction. That's going to guarantee a positive width. They're just guaranteeing that we find the difference between the two functions, that it's always positive. Okay? Well, you could try and work with that, but you'd really need a calculator to do that, or you'd have to come up with some piecewise functions. Okay? It would be a lot easier if we went through and we said, okay, I'm going to figure out what each one of these looks like. How can I guarantee that I find the area on this particular interval? So sine of x is pretty easy. Hopefully you don't need to use a calculator in order to figure out what the cosine of 2x looks like. What happens to the cosine curve when you multiply the x by a 2? Okay, it's a horizontal shrink. It speeds up the cycling time. It changes the period. Period changes from 2 pi to just pi because it cycles twice as fast. So this is going to start up here, 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 and here. It's going to finish the cycle in half the time. So notice what sine of x minus cosine of 2x would mean. It's the difference between these two function values. Okay, it would be the difference between these guys and the difference between these guys. But if the sine is first and we're subtracting the second one, sine minus cosine, bottom minus top, that would give us a negative value right there. The absolute value just guarantees that it's positive. Okay? Works really well right here. Sine's on top, cosine 2x is on the bottom, so that would guarantee us a positive there. So we can find the same answer by breaking this up like we did before. Let's draw a representative slice right here and a representative slice right here. Top is cosine, bottom is sine. Plus what we get over here, this would be the integral, let's see, top is sine, bottom is cosine 2x. Okay. Now I just need, well, let's see, I can figure out a couple of the limits. For this one, we're going to start at 0 and we're going to go to this intersection point right here. And for this one, we're going to start at that intersection point and we're going to end, it said end at pi halves. So I've got that one. I need to know where they intersect. Does anybody remember how to find out when the sine of x is equal to the cosine of 2x? Double angle. Yeah. So when the sine of x is equal to 1 minus 2 sine squared of x, which I'm going to make it look like this. I'm going to move those over to the other side. So this would be 2 sine squared of x. Let's see, plus sine of x minus a 1 equals 0. So this would be 2 sine of x, and that would be sine of x. And I need a 1 here and a 1 here, minus here, plus here. So I'm solving when the sine of x is equal to 1, and I'm solving when the sine of x is equal to positive 1/2. And where does that happen? Say pi 6. Happens at pi 6. Okay, this intersection point right here is at pi 6. So then we've got everything we need to finish this off. Whoops. This would be from 0 to pi 6, and this would be from pi 6 to pi halves. Okay? Any questions? Good review of some trig there. This isn't in that interval.
Isn't that negative though?
What?
The sine of x equals 1, isn't it negative 1?
Oh, -1, yep. Okay. But it wouldn't be on that interval anyway, right?
And then we could just multiply by 2.
Oh, wait a second.
Do what?
Can't we just find those two and then multiply it all by 2? Or are we going to find? Oh, sorry.
Just 0 to, yeah. Yep. Just 0 to pi halves, not 0 to pi.
If we were going to pi, couldn't we just find 0 to pi halves?
So Juan points out if we were going to
That's what I thought we
pi,
were going to do.
couldn't we just go from 0 to pi halves and then double the answer? Yep, that would work fine because of the symmetry here. Everybody good? Okay, so let's take a look at these last couple. We're going to set these up. I don't think we'll have time to do all of these, but we can at least set them up. It says find the area. So if we take a good look at this one, draw a rectangular slice. Do I have the same function on the top the whole time? And same function on the bottom the whole time? I do. So we could do the integral from negative pi half, whoops, that's negative pi, to 0. Top function would be 0 minus the bottom function, 3 sine of x square root 1 plus cosine of x dx. Or, what would maybe be a better way to set that up? Yeah. What if we went from 0 to negative pi? What if we integrated in a negative direction and then put a negative in front of it? Wouldn't that do it right here? Well, if we put a negative in front of that, I mean, don't we get the same thing here? So we could integrate from 0 to negative pi, and then this would just be, put a negative in front of that, 3 sine x square root 1 plus cosine x. Looks a little bit better. How do you do the problem, though? How do you find the antiderivative? Very good. What would u be? 1 plus cosine x, and du would be negative sine x dx. I don't need the negative, and I do need a 3, so I'm going to multiply this by negative 3 du equals 3 sine x dx. And then you can finish it off, right? Okay. Okay, would you set one up for that one? Representative slice. Same function as on the top and bottom the whole time. Interval starts here and goes to there. 0 to pi. What's the top? 1. What's the bottom? Cosine squared x dx. Sure you can. 1 minus sine, or 1 minus cosine squared is sine squared x dx. Find that answer, you've got your answer. Didn't we do this antiderivative the other day? Look in your notes, power reducing formula. Okay.
So 1 minus cosine
Yeah.
over 2.
So we wrote this as 1 minus cosine 2x over 2 dx, and we found the antiderivative for that, so that's how I'd evaluate that one. Okay? Any questions?
What was that, the power?
This is, we call it a power reducing identity. Okay. And you'll use those in 1220. Okay, now let's look at the very last problem, which if we looked at that at the beginning of class, that looks pretty wild. But look how this is written now. The trouble we had before, or at least a little bit of trouble, was rewriting these in terms of y, because we knew we were going to slice it perpendicular to the y-axis, so that our slices can get thinner and thinner in the y direction, so we've got a differential of y. On this one, we're all set up to go. What's the key instead of top minus bottom? Right minus left will give you a positive quantity there. So the right function is this one right here. So we're going to do 12y squared minus 12y cubed minus the left function. And again, I'd put that in parentheses. So there is our width, our positive width. We're guaranteed that's positive. And if we do these slices thinner and thinner and thinner, that gets thinner in the y direction because we're perpendicular to the y-axis, so that's a dy. And limits of integration. 0 to 1. Start slicing at y equals 0. Stop slicing when you get to y equals 1. So 0 to 1. 0 to 1. 12y squared minus 12y cubed. 2y squared plus 2y dy. Put a couple of those together. Do the integration. There's your answer. Okay? These are really good things. You're going to have to know these for the test on Thursday. May need to know them for the final. Absolutely, you will see these techniques again when you take 1220. Okay?
Memorize the power reducing formulas?
What's that?
Yeah.
Should we memorize the power reducing
Not for my test, but I would lock those away because you will see those power reducing formulas again. Okay? All right.